Right, now we're going to have a wee look at symmetry. There's two different types of symmetry we look at with objects. One of them is line symmetry. How many lines of symmetry does a shape have? And the other is rotational symmetry. We call it order of rotational symmetry. So if we start off with line symmetry, we're starting with the first shape, which is clearly a star. You can see it's written there. How many axes of symmetry that's the same as lines of symmetry can we find? Clearly there would be one down there. I think you're asked to mark them in blue. So if you've got a blue pen, you might like to use your pencil still in case you make a mistake. Marking in all the different axes of symmetry. So you can see there that it has 5 lines of symmetry. Now, order of rotational symmetry, the best way to look at that is use your tracing paper, trace around your shape, try not to waste the tracing paper, put your pencil in the centre where the centre of rotation would be. It helps if you write T for top, so I know when I'm back to the beginning, because the rotational symmetry is how many times, just gently hold that, would that shape map on itself if you were to turn the piece of paper around once and get back to the beginning. So you can see the T for top. Let's turn it very gently. It fits once, twice, 3 times, 4 times, and 5 times, and I'm back to the top. So order of rotational symmetry is the number of times it fits on itself in one complete revolution, one complete circuit. The answer is 5. Add those together and that gives you what we call the total order of symmetry. So a star is quite symmetrical. If we take another shape, we could perhaps try this parallelogram here. Looking for mirror lines, you can notice if you actually use a ruler or a mirror, you can notice that actually that's not a mirror line through the centre. It's not going to map on itself, and same with putting one through there. If you look, it's not going to give you a symmetrical shape. You could try on the diagonal. Not sure if you can see in there exactly, but it's not actually going to give you a symmetrical shape. So if we're talking about F, we might want to call that the parallelogram. You can make up names, we're not worried about the names. But there are no axes of symmetry. Let's just have a look at the order of rotational symmetry. So how many times it will fit on itself in one complete turn. It's really important you know where the top is. We just estimate roughly where that centre is and just gently turn it. Nope. Now that would be once. I'm not back at the beginning yet. Nope. Back to the top, and it fitted in twice. 0 plus 2 equals. So you can have a go with all of these shapes now, working out how many lines of symmetry and the order of rotational symmetry. You'll notice that every shape should have order of rotational symmetry at least once. If we choose a shape that we think doesn't have many, so maybe this one here, I doubt there's any lines of symmetry. I certainly think there isn't. And we have a think about rotational symmetry, T for top. And just gently holding my pencil. It's not going to fit on top there, or there, or there, but it should be back to the beginning there. So only one. So for G, there is only one order of rotational symmetry, and of course every shape will have at least one, because every shape will fit on itself at least once. That shape, no axes of symmetry, so that's a total order of symmetry of 1, not very symmetrical at all. We say a shape has rotational symmetry if this number in this column is bigger than 1. So if it's bigger than 1, then we say it has rotational symmetry. You could call that a knot or some other name for it. All right, you try the rest of them.